Hi everyone, my name is Sidhanth Mohanty, and today I will tell you about weak Poincaré inequalities and simulator annealing. This is based on joint work with my wonderful collaborators, Brice Huang, Amit Rajaraman, and David Wu. Okay, so as motivation, consider the problem of sampling from a high dimensional distribution mu with an efficient algorithm. So this sort of a problem comes up a lot across various algorithmic domains and is useful for a wide variety of downstream applications to optimization, inference, estimation, integration, and more. Okay, so just to get a sense of what kinds of distributions we can efficiently sample from, let's consider the class of strongly log concave distributions. So a distribution mu, which has density e to the power minus v of x, is called strongly log concave if this function v is strongly convex. And in particular, its Hessian is uniformly lower bounded by a positive scaling of the identity. The picture you should have in mind for a strongly log concave distribution is a bell curve, or more generally, distributions that look like Gaussians. In this talk, we will refer to the function v as the Hamiltonian of a distribution. And a classical result says that such distributions can indeed be sampled from efficiently. I would recommend the book of Sinho Chui for a detailed treatment of how one does this. Okay, so now let me tell you all of a very different kind of distribution, which is going to be the main subject of of study in the stock. It's going to be a good test bed for the kinds of things that we will study. So let me introduce the spherical p-spin glass. In the spherical p-spin glass, the Hamiltonian is a random degree 3 polynomial whose coefficients are independent Gaussian entries. And just to get a sense of what this distribution looks like, when beta is equal to 0, this is the uniform distribution on the sphere of radius root n. But as you increase beta and send beta to infinity, the distribution is far from uniform. Uh, for large beta, the distribution is supported on approximate maxima of the Hamiltonian. This problem is highly non-convex and is very multimodal, such as the picture that we have depicted in 3 dimensions at the bottom of the slide. And in particular for large beta, this distribution could be highly non-trivial to sample from, given that the number of modes is even exponentially large in dimension. Okay, so now let's talk about how one actually samples from probability distributions. There is more or less one standard paradigm to sample from a distribution, and this is the Markov chain Monte Carlo paradigm. And the paradigm entails designing a Markov chain P whose stationary distribution is the target distribution mu that we care about sampling from. And the algorithm is to simply run the Markov chain for time t, starting at an arbitrary initialization x0. Okay, and the algorithm simply outputs xt, which is the point that your Markov chain ended up at after running for t time. And the hope is this random output xt is distributed according to the target distribution mu. So now let me introduce the notion of mixing. We say that a Markov chain P mixes in time t if the total variation distance between xt, the place where the Markov chain ended up at, and mu is tiny regardless of where the Markov chain was initialized. Okay, so this sort of worst case mixing guarantee seems very appealing because it tells you that no matter where you initialize, if you run this algorithm, you do actually successfully sample from your distribution of choice. But actually, a lot of times, many Markov chains that we encounter both in theory and practice do not enjoy worst case mixing guarantees. So in this talk, our goal is going to be to try to understand when it is possible for a Markov chain to mix from a warm start or a good or random initialization, even when it does not mix from a worst case initialization. And what are some mathematical tools that one can develop for showing guarantees of this nature? So, our test bed for developing these tools is the p-spin model. And this is because it has some uh, desirable properties for studying this phenomenon. In particular, there exist choices of the parameter beta from a few slides ago, which I will refer to as the inverse temperature, for which the Markov chain mixes slowly from a worst case initialization. But also, if you initialize the Markov chain randomly, then it is predicted to actually work and successfully sample. And today we will be studying a variant of the random initialization scheme, and it's an algorithm known as simulated annealing that's used very widely across various domains. And it is a way to devise a good initialization for a Markov chain. Okay, so now let's get some of the basics down. Which Markov chain are we going to study, and how are we going to sample from this spherical p-spin model in particular? So we will be studying a Markov chain known as the Langermore diffusion chain. So here I can describe the chain via what it does when you're at some point xt. What does a single random step look like? Okay, so you compute the gradient of the Hamiltonian at the point xt. Now walk a tiny bit in the direction of the gradient. That's what the minus gradient of v of xt dt term is telling you to do. And then add a little bit of Gaussian noise. And that's what the square root 2 dbt term is telling you to do. So this is a continuous time description, but uh, if you'd prefer, here's a discretized version where at time t plus delta for a tiny constant delta, you take xt and perturb it by moving um, a delta amount against the direction of the gradient and adding a Gaussian of variance roughly to delta. Okay, so this particular Markov chain can be proved to have stationary distribution mu, which is e to the power minus the Hamiltonian, or rather the distribution proportional to e to the power minus the Hamiltonian. And you should think of this Markov chain as basically performing stochastic gradient descent on the cost function b. Okay, so now let me describe the simulated annealing scheme, which is a way to devise a good initialization for Langermore dynamics. So given this distribution mu, which is described by the Hamiltonian b, let us consider a whole family of distributions that interpolate between the uniform distribution and the distribution mu we actually care about. And in particular, we're going to define mu beta as the distribution described by beta times the Hamiltonian, where the Hamiltonian is a scaled down version of the original Hamiltonian. And when beta is equal to 0, you can see that this is the uniform distribution. But the sampling problem could be easy or hard depending on the exact structure of B when beta is 1. So the idea of the simulator annealing algorithm is to initialize at beta equals 0 and then slowly increase beta over time. The hope is, even if it's hard to sample from some mu beta from a worst case initialization, maybe if you were initialized at a slightly smaller value of beta, you do sample. So just to give an illustrative example, here's the depiction of what a certain bimodal distribution looks like when beta is equal to 0.1. And here, the two modes are like fairly well connected. So you could hope that running the Markov chain does indeed sample from this distribution, even from a worst case initialization. But now let's say you start with a sample from mu beta for beta being 0.1, and then slowly increment beta. Then you get distributions where the two modes are more and more separated, and worst case mixing is likely not going to be true. But since you initialized at a distribution which puts equal mass on both modes or around both modes, you would hope that running the Markov chain still nevertheless samples from this good initialization. So this is a fairly natural algorithm, but despite its very widespread use, there are actually very few efficient guarantees. And today we will talk about some guarantees that we could show for the spherical p-spin model for the simulator annealing algorithm. Okay, so in the examples that we considered, in the case of strongly log concave distributions, you could simply run the vanilla Langevin dynamics algorithm and from any initialization, and it would indeed mix fast and give you a sample. But the terrain for the spherical p-spin model is a little bit more complicated. So let's build up the picture of what we do know for sampling from this p-spin model on the sphere. Okay, so this model was actually first studied in the context of physics, and in particular, uh, in a paper of Crisanti, Horner, and Summers, they predicted using non-rigorous techniques that there is a threshold value for beta, denoted beta SH here, known as the shattering threshold, below which Langevin diffusion initialized uniformly at random on the sphere should indeed mix to the Gibbs measure. And the prediction also was that beyond the shattering threshold, the solution space looks very complicated and that sampling is likely hard. And they also predicted the existence of a different threshold, which is below the shattering threshold, which here is denoted beta pi. And the prediction is that under this threshold, Langevin dynamics would mix rapidly from a worst case initialization. But above this threshold, there are actually states at which you can initialize where Langevin mixes slowly. And these states, you should visually think of them as being these tiny bubbles surrounding the big mass in the middle. And the intuition you should have in mind is that if you initialize randomly, you actually very likely end up in the big mass in the middle and hence do mix fast. And only recently, in a paper of Huang, Montanari, and Pham, was it proved that there is another algorithm, not the Markov chain, but something known as algorithmic stochastic localization that can sample in a temperature regime beyond this beta pi threshold. And in this work, we proved that simulated annealing also actually breaks this worst case beta pi threshold and samples up to the threshold matched by the work of HMP. Okay, so today I won't really have time to tell you all too much about the proof, but in the rest of the time, I hope to introduce some of the conceptual ideas that were studied and introduced in our paper. So let's revisit the basic question of how one proves worst case mixing time bounds. So usually worst case mixing bounds are proved by first showing that for some appropriate distance function, if you are at any distribution nu, if you run the Markov chain for a single step, then the distance to the stationary distribution contracts by a 1 minus 1 over polynomial and n factor. And this paradigm has been extremely well studied over several decades, and people across various research communities have developed a large number of tools to prove this kind of a statement for a wide variety of Markov chains to solve many different sampling problems. Okay, so maybe let's be a little bit more concrete and talk about a particular popular distance function that is employed. And this would be the chi-square divergence. And this contraction in chi-square divergence is what is known as a Poincaré inequality. So just to reiterate this fact, we say that a Markov chain satisfies a Poincaré inequality if running a single step shrinks the chi-square divergence to the true stationary distribution, no matter what distribution nu you initialize at. Okay, and a Markov chain satisfying a Poincaré inequality is equivalent to its transition operator having a spectral gap. That is, a separation between the largest eigenvalue, which is equal to 1, and its second largest eigenvalue. And to just describe what a large spectral gap means more combinatorially, it means that every set is expanding. There is no set in the of states in the state space that has small conductance. Okay, so uh, all of this seems like a very worst case guarantee. We're saying for a worst case initialization, you get this contraction. Or for a worst case chosen set, you still have good expansion. So how can we go beyond worst case mixing? And in particular, is it possible to develop tools that can let us understand situations where you mix only from some nice set of initializations? Okay, so it turns out that you can achieve this if you can prove the following weaker version of the contraction statement alluded to in the previous slides. So consider a contraction statement of the following form. You're at some arbitrary distribution nu, and you run the Markov chain starting at nu for one step. You would like a statement where you can say that after you ran the Markov chain for one step, the new distance to the target stationary distribution mu is the old distance times a 1 minus 1 over poly n shrinkage factor. But plus some additional defect term, which possibly depends on the distribution nu. And in particular, we say that a Markov chain satisfies a weak Poincaré inequality if for any initialization you satisfy this distance contraction with a defect for the chi-square divergence. And if one could prove that for some given initialization, the defect is small along the trajectory of the Markov chain, then it would actually imply that you do have a polynomial time sampling algorithm. Okay, so far, this idea of considering contractional defects or Poincaré inequalities that allow for a little bit of defect is not new and has been studied by several papers from the late 90s and early 2000s. Okay, so in our paper, we actually give a generalized framework for proving weak Poincaré inequalities for various Markov chains and in particular for Langevin dynamics, which generalizes some of these local to global frameworks that have been pretty influential in the Markov chains literature in the last 6-7 years, such as spectral independence, localization schemes, and more. And of particular interest to analyzing Markov chains from average case initialization or for analyzing simulated annealing, we prove that if your distribution and Markov chains satisfy a weak Poincaré inequality where the defect function is some tiny epsilon times the oscillation of the function f squared, then it implies guarantees for the annealed version of Langevin diffusion. And here you should think of oscillation as being some measure of how much the function fluctuates. So more concretely, it is the maximum minus the minimum value that the function takes, plus the maximum value of the gradient that the function can possibly achieve. Okay, so since the definition of weak Poincaré inequalities was a little bit abstract, on this slide, let me give two concrete examples of how you may satisfy a weak Poincaré inequality. So imagine the distribution that you have at hand is a mixture of two strongly log concave distributions or a mixture of two Gaussians even. Then you don't necessarily have contraction from like a worst case initialization. But if the initialization is symmetric, that is, it puts equal mass on around both of these modes, then the defect to satisfying Poincaré inequality is even 0. If it's approximately symmetric, that is, if you put 51% of your mass on one of the clusters and 49% of the mass on the other cluster, then your defect is some small number which depends on the discrepancy between 51% and 49%. Okay, as just to consider yet another example, let's say you have a strongly log concave distribution, but then it was perturbed by a tiny blip or a tiny amount of probability mass somewhere far away from the cluster. In this case, if you have epsilon mass that is far away from this single cluster which does satisfy true Poincaré inequality, then the overall distribution and in particular Langevin diffusion for this distribution satisfies a weak Poincaré inequality where the defect is epsilon times the oscillation of f squared. And that's it for the technical portion. I want to end this talk by telling you all a couple of open questions. So recall that we were able to show that simulated annealing successfully samples from these p-spin models up to some threshold that is between the worst case threshold and the shattering threshold. And our result is likely not tight. And even though we're within a universal constant of the actual correct answer, the shattering threshold, uh, there are actually barriers to breaking past the result that we got. And the natural open question here is whether one can close this gap. A related question is to extend the results from this paper from the sphere to the hypercube. The reason this is interesting is because when spin glass models were studied in a physical context, they were actually studied with the hypercube as being the domain of interest, since that is a setting that could possibly say things about um, magnets or other properties of materials. And the spherical setting is more so a mathematical simplification. Okay, so now just to go in a pretty different direction, the broad direction here is whether we can give provable guarantees for simulator annealing in the context of inference. But just to tell you all a concrete problem, consider a graph drawn from the stochastic block model. So in the stochastic block model, each vertex is colored either red or blue. You have some underlying set of vertices, colored red or blue. And then between a pair of vertices that have the same color, you put down an edge with slightly higher than average probability. And for pairs of vertices that have opposite colors, you put down an edge with slightly lower than average probability. And now I conceal the colors and give you the graph, and your goal is to infer the hidden coloring. It seems like if you run the simulator annealing algorithm to sample from the posterior of this particular model, then it appears to perform optimally, though we currently lack theoretical explanations for why. And now another question, which is yet in different territory, is whether one can get improvements for guarantees for worst case approximation algorithms using Markov chains from non-worst case initializations. And just to give you all a concrete problem here, if you consider the max cut problem in a graph, then a natural semi-definite program plus half-space rounding gives you a 0.878 approximation to the max cut. And it is a conjecture that if you have a graph that is bounded degree, then one should be able to approximate the cut up to a 0.878 plus an additional 1 over square root d advantage factor. And in a recent work of Shea and Kothari, they proved that performing some kind of local updates to the solution you got from your STP lets you get a 1 over d squared advantage. Now, running annealing with the cut being the objective function seems like a natural principled way to perform local updates to improve the solution. So the question I have here is whether running MCMC initialized at the STP solution actually let you get this 1 over root d advantage. And in terms of theory building, this and the previous question are also natural extensions to our results, because in this particular work, we were able to give conditions under which annealing has sampling guarantees from non-worst case initializations. But can we say anything about inference or optimization guarantees? Uh, Thank you for watching. And if you have any questions, you should feel free to email me or any of my co-authors. Thank you.